Hi everyone, I will mention about derivative in this video. As you know, derivative is defined with this limit. As you know, without limit, the rational expression of ft0 plus delta t minus ft0 over delta t, or ft minus ft0 over t minus t0 is average speed between the t and t0, between the variable t and t0. Let's look on a sample function. If you define this function as time, as the function of time, and here is speed, and this axis is time, this function defines the change of speed over time. And as you see, between the interval and the interval AB, the speed is changing more speedy, but in the interval, this interval, the speed is lower than the previous interval. And in this interval, you may say that the speed isn't changed. And without limit, this is average speed. But as you know, there are lots of instantaneous speeds also. We can mention about instantaneous speed also. For example, at this point, at this instant, at this fixed time, you may say that the speed is 0. But here, the speed is not 0. And while this on this point, on this time, the instantaneous speed is lower than at this time. How can we measure the instantaneous speed? Our video subject is this. We may understand intuitively that on some instant points how the speed change. But how can we measure the speed mathematically? This limit will help us to measure the instantaneous speed. And please forget the function of time. This function is defined of time or speed. Just we think the function between two variables, and we don't say the speed as a physical meaning. We just say the speed of changing value. Let's start one of my previously designed application for this purpose. Yes, my application is here now. You can also find this application in my GeoGebra Tube profile. You can find the link and the explanation of video. Now I am trying to measure the speed of this function, speed of changing value of this function at t0. t0 is 0.6. The function is x cube, and just I am creating the second between t0 and t0 plus delta t as written here. this is the second, and delta t is approaching to 0, begin approach, and while as defining in this limit, while delta t is approaching to 0, our second, which is defined by this rational expression, this second changing into a tangent at t0, and the slope of this tangent will define our instantaneous speed. Let's observe again. And there is one important thing which I need to remind you. As you remember, limit is defined by left limit and right limit. As you know, this limit exists if both delta t is approaching to 0 from left and from right. At this time, this limit exists. Let's observe approaching from left also. This red line represents the second approaching to delta t, approaching of delta t to 0 from left. The blue line is the second approaching delta t from the right, delta t to 0 from the right. And how can we say that this limit exists? Both this blue line and this red line meets. If these two lines meets, we can say that this limit exists. Let's show the trace of seconds and begin approach again. Oh, let me start from the start. During the approach, my seconds leave a trace, and you can say that this limit exists if two traces meets. Stop. Begin approach again. Yes. Please focus on here, closer to the point t0, in this case 0.6, and you can say that these traces will meet. Stop. Layer trace and height trace. And so we can say that the derivative of x cube exists on the point 0.6. Let's try another function, sine of x, and I can change the point, which I will look for the derivative. Again, begin approach, and you can also observe that these 2 seconds meets on this tangent position. So the slope of this tangent will define instantaneous speed of changing value of the function sine of x at the point 1. Of course, the subject of this video is not how can we evaluate, calculate this slope deductively and algebraically. And let me mention about which cases we cannot find the derivative. First, a popular example, absolute value of x, and my point is firstly my point is 1. Back to start and begin approach, and there is nothing changing because all seconds approaching to 1 and closer to 1 are constant, so have constant slope. So the tangent also has this. The tangent also has the same slope with the seconds. And stop approach, and let's set the point different from 1 as 0 and begin approach. In this case, you can see that again we have constant slope with secant and tangent, but there is something interesting here. Here, left derivative is constant as with this as the slope of this line, and right derivative is also constant as the slope of with this line. I am not wondering what is the slope, but I am sure that this limit doesn't exist for this function at the point 0. So the absolute value of x is not differentiable at 0. This case was the popular case we know. I will show you a new function, 1 minus x minus 2, a different function, an interesting one, x minus 2 to the 2 over 3 and again to the three over 2. I just wrote the brackets wrong. Let me write again. 1 minus x minus 2 to the 2 over 3. I prepared this function before. 3 over 2. Yes, my function is this now, and I will search the derivative on the point 2 and begin approach, and you can also observe the traces. What is going on now? Yes, you can say that left seconds, the trace of left seconds and right seconds doesn't meet in this case. So this limit doesn't exist for this function at the point 2. So this function isn't differentiable at 2. Of course, stop, hide trace, clear the trace. Of course, this is just the case for the point 2. You can also observe another point of this function. What is going on another point at another point? Just focus on the closer intervals of the closer neighborhood of the 1.8. Begin approach again. As you see, in this, even this function, a suitable point, there are also suitable points which the function differentiable. This function is differentiable at 1.8, and the derivative is measured by the tangent of here. But at 2, we cannot mention a suitable tangent of this function. So mathematically, since this limit doesn't exist, mathematically this function doesn't have a tangent on the point 2. But of course, you may say that since this limit exists from left and from right, this function has left derivative and right derivative. Okay, I hope when the derivative exists and when the derivative doesn't exist is clear by this video. You may say that a physical definition of the curve of the function, if the function has a tip on the point, at that point the function don't have a derivative. Thank you for watching.